All right. Well, good afternoon, everybody, and welcome back to the next week. I have no particular announcements, just please, one thing to be careful about with the project. We do assume that the project, that your directory structure in the project will be as it was in the shared, in the skeleton that you imported. So there's a proj1 directory under whatever your working directory is. Please don't reorganize that. That will make it, that'll make it difficult for the it'll make it impossible for the autograder to do the right thing. Autograding, as you may have noticed, there is a portion of the project that requires something that obviously can't be easily auto-graded. So we will be doing that part separately. It'll take a bit. You won't get instantaneous feedback as to the entire score. As to when the autograder will be run, again, I am trying to discourage people from relying on it for debugging. You've got plenty of sample tests. I'm hoping that you're adding your own because the sample tests are not complete. And you should have a pretty good idea of whether your program is working by the time you submit it. So if not, if any of this is causing problems for you, please let us know so that we don't make it a last minute thing trying to scramble and fix whatever problem you have. I will be releasing project 2 soon after you turn in project 1, but not that you have to start working on it immediately, but it'll be available. Okay, in that case, let's see, seeing no hands, why don't we just get started with the topic today, which is the bulk of static semantics, having to do with scope rules and their implementation and type rules and their implementation. Well, we had a brief sort of overview of this last time. Let's do a little bit more detail this time. So if you have any experience with a number of programming languages, you will have found that there are various ideas about what the scope of a particular declaration is, where it starts, where it ends, and so forth. The one you're familiar with, most likely, is Java or C++, where a member of a class includes the entire class, whereas a local variable declaration, the scope starts at the declaration itself and proceeds from there. So anywhere before that, the thing is not declared. Now and then outside classes, you have a phenomenon that you see in C and elsewhere here, where if you want to use something before it is defined, you have to give what is sort of generically known as a forward declaration. So C and C++ have this notion of declarations versus definitions. So for example, this is the declaration of a function f that takes an integer as its argument and returns an integer. It contains no body. This is a definition of f. It contains both the declaration part plus a body. And if you want to use a call to f, say here, then you must have declared f up here. Now, likewise, if you want to use a class in C or C++, you must have declared it to be a class. Even though you haven't said what's in it, you have to declare nevertheless that it is a class so that C and C++ know that this, well, C doesn't have classes, it has structs, but but you know that this C here validly refers to a type of some kind. And then only later do you need to actually declare it. So this is in contrast to Java again, where a class, the scope of a class, in fact, includes the entire package that you're in, all the entire file that contains the class, plus all the other files in the same package. Now, as you also know, it's possible to have another variation. But basically, right now we're just looking at variations in languages. You know that you can define the same name with two different argument lists, two different lengths of argument list, or two different types of the variables in the argument list. We call that combination of name and argument types the signature of the function in Java and C. Or yes, in Java and C++. But it doesn't include, but despite the fact that these declarations include return types, that's not considered part of the signature for the standpoint of overloading. And instead, so that this particular combination of declarations won't work. You will not be able to tell, because Java and C could not tell which one you're calling at any given time. On the other hand, there are other languages, such as, for example, the Ada language, where this does work. I can define two functions and with different bodies and different return types, but the same name and the same input type, and everything will work. If for example, I have a statement like this: A is an integer, I assign G2 to it, it will call this first function and do the right thing. And in this case, it will call the second function. In the case of float, it'll call the second function. It's an interesting variation. Somewhat controversial at the time it was done, but there you go. Now, you'll hear there are actually some rather obscure cases in C++ where you also do disambiguation as a result of what type is expected. So here, the type of G, of the call to G, is determined by context. It's in the context of an integer, of an assignment to integer or to float. So by context, we know what its return type is. Therefore, we can look it up here. Now, in C or C++, you generally don't do that. You do it just on the basis of, or you do the decision of which to choose just on the basis of the argument types. Okay, so that's usually the rule, but in fact there is one obscure case in C++, and some of you might have some fun looking to see if you can find it, where in fact the context actually does determine what declaration you find. I'm not going to tell you, you can find it yourself. Oh, I'm sorry, one final thing. I'm calling this, I'm including this in the section on scope rules because you sort of think of it as, here I've got two declarations of the same thing. Turns out you can also, obviously it involves types because we determine on the basis of what the types of the arguments are. And in fact, there's actually a way of thinking of these two things, these two declarations of functions as being part of the same, just two pieces of the same declaration, in which case the function G has a bizarre type called a conjunction type that is both a function from ints to ints and a function from floats to floats. But that's a rather esoteric topic that we're not going to pursue. It's just an interesting alternative way of looking at a a bunch of overloaded function definitions as being a single definition. All right, now, you have been used to, with Java and Python and Lisp, you've been used to something that we call static scoping, in which the declaration, in which the scope of a declaration is determined by the text of the program, and the declaration that applies to a particular variable depends on where you are in the program. But in fact, a somewhat older, well, I don't know if it's older, but let's say nearly as old scoping rule was that of dynamic scoping, where the use of a variable refers to the most recently executed and still active declaration of that variable. So for example, in this fictional language, which looks sort of like, I don't know, Java, I suppose, but isn't. I might have something that looks like this. I've defined X in a number of places, always as local variables, but I haven't defined it. I've used X in G, but I haven't defined it anywhere in G. And so of course in Java, this would be, or in Python, this would be an error. It would say X is not a defined quantity when it gets down here to G. On the other hand, with dynamic scoping, the rule would go like this. If I execute F1 right here in the main program, then it comes down here. I declare X to be an integer. I call G. So when G executes that first time, X, the latest declaration for X will be this one, int X equals 10, and this will print 10. When I then call F2, what will happen is that we'll set X will now be a string. We call F3, which defines X to be a double. However, F3 then exits so that the declaration of X as a double is no longer active. But the latest declaration is then still the declaration of X as a string. We call G, and it will print the string hello. That's dynamic scoping. And you can see that if you're a compiler trying to figure out, say in this procedure G, what should I do? Should I be prepared for an integer or a string? It will say the answer will be yes. You know, I mean, you don't know what X refers to. It's coming from somewhere, you have no idea where. And in fact, if this program is compiled separately from another program that uses it, there might not be an X in sight at the time that you compile this thing. So it obviously leads to a much different set of problems. Turns out it's not all that difficult to implement, but it's rather difficult to analyze, and it's rather difficult to implement efficiently. C++ namespaces are like dynamic scoping. No, I wouldn't say so. It doesn't, the order of execution does not matter in that case. I'm sorry, I'm reading a question on the chat. Isn't F3 executed later and then? No, I'm sorry, we'd better talk about this offline because I'm not quite sure what you're getting at. All right, now another dimension in the language design universe is whether things can be declared implicitly or explicitly. Now, Java and C++ generally require explicit declarations of things. That's actually less true more recently when certain kinds of implicit definitions are possible. but well, we perhaps will see that at some point. The C language is kind of lenient. If you say foo of 3 at some point in your program, and there is no declaration of foo, it'll just assume, oh, well, foo must be a function that takes some arguments and returns an integer. It just assumes that it must be an integer. And as for which arguments it takes or what types of arguments it takes, it basically says by default, well, anything. It might take anything and return an integer, which is kind of strange. But then C is kind of rough and ready when it comes to compile time correctness. And so there's no explicit declaration of foo, and yet this will compile properly. Of course, eventually, when you have a program that you expect to run, there's got to be some definition of foo, but for the time being, it doesn't matter. C++ decided to get a little more stringent about that. You have to say that foo is a function, that it takes an integer argument, returns whatever it returns. And you also have to say whether it's a function that's defined in the same file, or that must be defined in the same file, or whether it's something that's globally available to other programs. Python has a rule that says that if you simply assign to a variable, if you mention a variable and assign to it in a function, then that's a declaration, that's an implicit declaration of the variable. Whereas Java and of course requires you to, and C and C++ require you to have a declaration for that variable. Now, Python, being dynamically typed, doesn't bother to ascribe any type to the variable. Fortran, yes, that's an oldie but goodie. Well, maybe not goodie. It's an oldie in any case. It will implicitly declare any variables you use, and it will also implicitly give them a type, which depends on the first letter of the variable name. So I through N is an integer, and everything else is a real number or a floating point number. Despite the fact that this is implicit, that you don't see anything, nevertheless, there is some sort of declaration. That is, the compiler treats an assignment as a declaration. It treats the appearance of the variable, the first appearance of the variable as a declaration, something like that. There is a declaration. It's just not written down. So that means, so even though the declarations are implicit, that doesn't mean that this is not a statically typed language. It means that it means simply that there are certain declarations that you don't have to write. All right, so let's look at the implementation issue. I said in the previous lecture that the idea is to take an abstract syntax tree, such as produced by the parser, and attach types to it, to its various uses. And that means that we'd like to attach to these variables that we get information about their types and other things, but not necessarily without, since we're doing this statically, without worrying about what the actual values are. Now, it turns out that you've already seen this in the form of the DREAD environment diagram. So, given, for example, a Python program like this, and by the way, this also applies to the old days when we used scheme, it would be basically the same. Yeah, I'm sorry, that should be x plus y, speaking of scheme. We have this program, and at the point that we execute x plus y, we say that there is an environment present at that time. The current environment has a value defined for y, which is 42, and it's nested inside another environment that has a definition of X as 3. And that's nested inside a global environment that has a different definition of X and a definition of F. Now, actually, I should say there's a little error here. In Python, the X and the Y would be together in one environment clause, but in other languages, it's a little different. So if I now take this environment diagram and I throw away the values from the execution and then replace them with some other information, like, for example, what type of variable this is. And in the case of Python, it's uninteresting. It's basically always any, or maybe a function of any to any. If we do that, then we have static information that's always valid whenever you are here in the program at the X plus Y. And this data structure is suitable for keeping track of, or for ascribing declarations to identifiers as you go along. So that's kind of an interesting little thing. We've basically taken a runtime, something that we know of, that will be formed at runtime. We've abstracted away values, and we've gotten this compile time data structure. The reason we can do that is that even though the values here change, the structure of this environment will always be the same. It will always look the same. It will always look like this, but with different values depending on how the thing is executed or when the thing is executed. All right, well, so much for scope and ascribing things to identifiers. The next issue is ascribing information to them, types to them. So the general idea of type checking is that we determine a type for every expression in a program. So expressions are not just variables, but also literals like 1 and 3, and also expressions like X plus Y. So everything basically has everything that is supposed to have a value or produce a value is given a type, a static type. And the nice thing about this, in the case of a language like Java or C or something like that, is that it allows the compilers to find errors and warn you about them before you've actually executed the program. So let me just ask you a softball question here. Give me an example of the kind of error that you can find by this kind of analysis. I will wait for somebody to chat or raise his or her hand. Int plus string. Yes. Well, actually, that's an interesting. All right. So we have an example, int plus str, which if we think of this in Python, I can interpret that either as he means an integer, or you mean an integer plus a string, which is an interesting case because, of course, that's valid in Java, but not in Python, and not in C. Or you could use it as the in Python it would be the type int plus the type str, which is in fact a plus applied to two types, which also makes no sense. So either way, yes, that's an example. And then, so if we gather together all such rules, we have, and here's another example down here, int x equals hello. That's exactly in Java, that would be flagged by the compiler as an error, an inconsistency between the type you said x had and the type that it actually has. Then we have a bunch of type rules refer to the rules in the language that say what the types of things must be. Now, I haven't really said in this slide well, I guess I've said in the first bullet there, I've implied that this is something that happens at compile time. But in fact, type checking is a concept that's applicable at runtime as well for dynamically typed languages. So for example, this business of int plus string would be found at execution time in Python, and it would be reported as a kind of type error. All right, so we use this, throw this term around, type, without really saying what it is. The classic definition is that it is a set of values, we call it the domain, together with a set of operations on those values. So fields and methods in a Java class correspond to the things that hold the values of objects of that class. And so a Java class represents a type of object that contains data, one piece for each field. And it contains operations that operate on things of that class. So then we have a type system is simply something that defines what types of things are and which operations are valid in which places. So the idea being that you make sure that operations, when they are applied, make sense. And if they don't make sense, then you somehow or other report an error, whether it be at execution time for a dynamically typed language like Python, or at compilation time. Now, of course, so it's a kind of correctness, but not necessarily correctness as defined by your program doing what you want it to do. It means that it's correct according to the rules, the constraints of the language. And in nice expressive languages, the idea is that this notion of correctness can be made to correspond to your internal notion of correctness. And so finding type errors is actually finding, is a sort of a baby form of finding logical errors in your program. Okay. So for example, if we sort of go down to assembly language, I can add both integers and pointers to functions are represented at the lowest level as integers, as integer strings of bits, basically a finite number of bits. And I can execute, this is i86 assembly language. I can execute things like this easily enough, and whether or not y is the name of a function or y is the name or y is a variable. So it's so in any case, it's basically the same thing. So as far as the assembler is concerned, everything is fine. It's at the higher level of the programming language that you're using that you're making an error. And that would correspond to a logical error in your thinking. All right, so what do we use these types for? Well, obviously the one big thing is in detecting errors and reporting errors. So such as the ones we've been talking about. It's also used for such things as, for such high-level concepts as the violation of abstraction boundaries. For example, one of the things that you do as a programmer is you designate certain things as private, meaning that it is your intention that they be manipulated only by methods within a class. And the type system, or something very similar to it, something, an extension of it, determines whether in fact you have incorrectly used a private field in that way. The other thing, and the more, I guess, the historically first use of this was in making compilation easier or making programs faster. So Python sees x plus y. If you looked at the code that actually gets executed when you say x plus y in Python, you would see that instead of just taking x and executing some add operation to get y, it first checks the type of x, it checks the type of y, it goes looking through various things to see what plus might mean for these particular types. It does a lot of work. Whereas if as in Java or C, the compiler already knows that x and y are, for example, integers, then it can eliminate all of that code. In the case of, so it can eliminate all of the code that was doing that checking, and as a result, it could make faster code sequences. And of course, in cases like, say, the oldies but goodies like Fortran, that's exactly what you want to do. In those days, you couldn't afford to spend a lot of time checking the types of things. You had to, that all had to be taken care of before translation. Otherwise, your programs would be too slow, because in those days, computers were measured in not gigaflops, but more like kiloflops. And so the people tended to be much more careful about execution time. Now in 61B, I at least in 61B make the distinction between static and dynamic types. I've been dropping those terms without definition up to now in this lecture, so let's define them. So I use the term dynamic type to refer to the types of values. And it refers to the type of it's a runtime notion in that sense. It's something attached to a value. Whereas a static type is something that is independent of any execution and attaches to an expression or variable. So if a language's type rules are such that there is a non-trivial set of things that the type rules that the compiler can enforce, we say the language is statically typed. Now, you have to be careful. That's why I use those hedge words, significant here or non-trivial, because one could argue that an assembly language is statically typed, because absolutely every quantity in an assembly language program is a bit string of some particular length, depending on the size of the register. And so, yes, everything is a word. And that is absolutely enforced by the machine. You never get anything other than words. But since you're using words to build other objects, there is no guarantee that you're using them consistently. That's not what assembly language provides. Now, C is often said to be, the typing system on C is often suspect to be absolutely technically accurate. I would say that the thing is that C says a lot of things, the C standard says a lot of things are undefined or erroneous, but it's just that the implementations don't check for that. So you get situations, certain situations where you can treat, for example, an integer as a pointer to a string. And although the C standard tells you that if you do that, you get undefined results, nothing will keep you from doing it. and you will generally get undefined results. Whereas Java is very strict in this regard. So it used to be, I mean, the early type rules were simply that the dynamic type of some value, of the value of some expression, always has to be equal to the static type of that expression. So we know so that the types and the type of the value is in fact the type of the thing that that yields that value or contains that value, as far as the compiler is concerned. So in Fortran, if the only kinds of integers the only kind of variables that contain integers are ones that are declared to be integers. Now, when we introduce in the object-oriented languages, we introduce the notion of subtyping, well, things start to get rather complicated. So we can define subtyping is a relationship between types, or a relation between types. It can define as an object of type X could be used when one of type Y is acceptable. This sort of the, this is often credited to Barbara Liskov and her co-workers. So the idea is that I can substitute wherever I'm required to use Y, if I can validly put in an X instead, then we say that X is a subtype of Y. That is, all of the features of Y that might be called upon are also features of X. X conforms to Y, or X extends Y in Java terms. Now, elsewhere in this lecture, I'm going to use just plain less than or equal to for this relation. I'm using it here to make it clear that we're not talking about numbers, we're talking about types. So this subtyping relation is a familiar kind of relationship. We say that a type is a subtype of itself. We define if X inherits from a type Y, extends Y, then X is a subtype of Y. And transitivity, if X, let's see, if X extends Y and Y extends Z, then X also extends Z. So these are, you can see this as your typical partial ordering of types. So this is all review. Of course, you've seen this many times before, having worked in Java. We have a situation here where we have these two classes. Class B extends class A. I've defined X to be an A, and indeed I can stick A's into it, but I can also stick B's into it, because the value that I'm sticking into X has a certain dynamic type B. But I'm allowed, since B extends A, I'm allowed to insert that into a variable of type A. So the general rule is that this is called, I'm calling this soundness. In Java, the rules of the language are such that for any expression, the dynamic type of the value of that expression when it's executed is a subtype of the static type of the expression. So it's some value that comes out of the, it's some value that has a type that extends the static type of the expression. The compiler, since it doesn't have the, doesn't look at the program execution, it looks only at the program itself, uses the static type for everything, and it assumes that the value is going to have this static type, and that's sort of that's sort of how the thing works. Every time I make a subclass, an extension, the only thing I can do is to add new attributes. I can add new fields, I can add new methods. I can never take anything away. That's why it's always valid. That's why this equation here is valid, because I can, if anything that has a certain static type, if the compiler can guarantee that that's going to work for that static type, it must also work for anything that can be stored or that can be returned from E, because anything that we can return from E has to be an extension, and the extension must have all the same fields and methods, or accessible fields and methods, as the original value, because the extension can only add attributes, it can't subtract them. If I add a method, or if I override a method, then the rule is that that the new method has to have the same requirements, the same signature as the old one, so that in fact any call that I make, assuming that something has the static type of E, will work even for things that are not exactly that type but are some subtype of it. All right, so that gives us these three sort of categories of language: ones that are statically typed, where all this type checking occurs at compilation time. This kind of type system can be kind of elaborate. I think we'll see one example a bit later on. We can have dynamically typed languages where all the type checking and so forth occurs at program execution time, and you can write programs that are perfectly valid, at least on some inputs, but not others. And that's, as a result, you have to do a little bit more testing of the programs in order to tell whether, in fact, they are sensible, whether their types are all compatible. And then you can imagine the language that we'll call untyped. And that, I guess, the only thing in that category that I really know is, or that I can really think of, is assembly language, where yes, there is a type, it's the type word, but that, since there's only one type, that doesn't really mean anything. And all of the type errors show up in weird executions. Bash is arguably untyped. I would argue, all right, so that's a chat thing. Stringly typed. Yeah. I think you'll find that there are certain things in Bash that are, that you can declare to have types. So it's sort of in a kind of a middle category. Dynamic, I would call it dynamically typed at worst, actually. Now, this has led, these, the two options, statically and dynamically typed, have led to what have been called type wars. So you have, so I'd say it's sort of mainstream programmers sort of go with static typing. And then there are a few people, such as folks who push maybe Python or Ruby or something like this, who argue that, in fact, dynamic typing is better. Why? Well, they'll give various arguments. The static type systems, because they're restrictive, there are certain programs you may not write, even though they might execute under, even though they might always execute correctly, they're nevertheless not legal, and this can sometimes constrain the things that you write, make them more awkward. They will say that it's easier to rapidly prototype things because you don't have to worry about figuring out exactly what you want the types of things to be. You can just plop them down and they will work, leading to what is called a technique called duck typing, where you define the type of things by what you can do to it, period. And and then all you have to do again is test to make sure that your program is actually doing that. Now the static typing proponents, and I think they're probably the majority, say that the advantage of static typing is that you catch lots of errors at compile time. Testing can only, the saying is that testing can only determine the absence of, the presence of errors, not their absence. Whereas with static typing, you basically make statements along the line that effectively amount to all possible executions of this program will work, or there are executions of this program that won't work. And that's a more sweeping and useful statement than this program may sometimes fail. Static typing also can avoid, as I said before, it can avoid certain runtime checking. It can make your programs faster and smaller, in other words. And the inflexibility that the dynamic typing proponents worry about, you can recapture by adding some elaborations to the type system so that it allows you a little more flexibility. Of course, all flexibility is results in complication. So here, for example, is what I have to say in Python to sort things. And here's what I have to say in Java to do basically the same thing. So this sorts, this thing will sort a list of things, or anything that behaves like a list that has a length and responds to brackets. And that has the elements of the list, where the elements of that list respond to this operator here, to this test, LT. Now to do something similar in Python, in Java, we have to write a declaration that looks like this. We say that V is a, well, in this case, I'm actually being more specific than Python. I'm saying V is an array of T's, and it takes, in place of LT, we have this comparison operator, and it has this rather weird type. It's a comparison of some type that is a super type of type T. And here is the rest of it. So you have to write this to get the anything approaching the full generality of the type of the sorting procedure over here in Java. Right. So all of our assumptions in Java are explicit. But of course, this particular syntax here will puzzle the beginner. You have to think about it a little bit to see exactly what this means. Now, I just point out in passing that, in fact, there's this other Java library routine for sorting. And it sort of says, if you happen to give me an array of objects that implement the comparable type, then I can sort for you. So this operation down here, comparable of X, convert, which is cast X to be a comparable, is of course something that can fail at runtime if X is a type that isn't comparable. And so this is in effect, I'm basically implementing dynamic typing in Java in effect. That's what's going on, because in Java, the type object takes care of anything that's a class. I see a comment here, static types are documentation. That's right, that's another argument made by static type proponents, that by adding types to things, you document more about what your program is doing, or how it is intended to be used. Now, what are these subtypes used for? Well, they in Java, one can provide an implementation of some set of operations. And one can also define a set of operations without actually implementing them. So you define a set of operations, give all their characteristics, but but make it possible to have multiple different implementations for them, while at the same time being able to check that any program that uses one of these things is in fact correct. So just to sum this up, we have basically relaxed the effect of subtyping is to relax the static type rules of Java by saying not that something has to be a specific type in order for my program to work on it, but it has to have a type that is a specific type. And then this is a here is a technical term. It means is a subtype of. So I'm saying, so for example, strings are a type of object. They're an extension of object. Therefore, we say a string is an object. Now, another way that we get this kind of flexibility from absolute static typing is by means of coercions, the purpose of which is to make it possible, is to cut down on the amount of writing we have to do. So we can write these things in Java. I can assign a character to an int, or an int to a float, and Java will automatically say, apply a conversion of one side to the other. You could also have written this explicitly as int x equals paren int n paren quote c, but this allows you to skip that. So you might think that this is just like the subtyping rule. It isn't really technically, because in fact there is an operation. Subtyping does not require you to do any conversion on the variables you're assigning, whereas this does, especially this second one here. So again, the idea of this concept, this coercion concept, is to avoid having to write out things that we already sort of understand. It's part of the zeitgeist, if you will. Everybody knows that integers, or some part of the integers, are a subset of the values of type double, for example. So why make it necessary to do this, to do an explicit conversion? It just clutters up your program. Now, normally in Java, one can convert floats back. There's a way of converting floats back into integers as well, and integers into characters. You can cast them the other way, but generally speaking, if you're going to do that, well, generally speaking, the coercions, the implicit things like this, where you don't have to write an explicit conversion, are the widening coercions, the ones in which you take a type like character that has fewer values than the thing you're converting it to, you're coercing it to, and you just do that coercion because you know that there aren't any problems with it. Whereas on the other hand, if we were to reverse this and have char, say char c equals, or char something equals x, there's a possibility that x's value is outside the range of characters. So this is a somewhat iffy conversion, and therefore is generally not automatic. In Java, it certainly isn't. And as usual, things get sort of complicated or messy, because there are cases like, for example, the conversion of ints into floats. That's something that you're usually you expect to be able to do, because you say because if something happens to be an integer, you may or may not write it with a decimal point. So why not consider, I mean, why not consider them to be the same, or why not consider integers to be a part of float? But as it turns out in Java, there are ints that are not exactly representable as the type float. That's because float does not has fewer than 32 significant bits. Nevertheless, this coercion for historical reasons and for convenience is still allowed. Likewise, conversions of long into double, even though long has 64 bits and double, well, 61 bits if you don't count the sign, whereas double has 52. So just to emphasize this, a few examples of things that are okay and things that aren't. These are, of course, not implicit coercions. These are explicit conversions, and they work. They are this thing, for example, y equals x is legal even though it might cause an error. So that's the difference between an implicit coercion, like y equals x, is considered to be an error. This is not considered to be erroneous at compile time, but might cause an execution error. So in effect, we've sort of turned this into a dynamic typing sort of thing. Sometimes it will work, sometimes it won't. And this is an interesting example from C++. C and C++ allow you to define things that are constant. So you can say that this pointer here, T star, is or this pointer T, I'm sorry, this type, const T star, means that you've got a pointer to an object of type T, and that object is constant. You can't assign to it. I can have, now normally you can coerce a T star into a const T star. In other words, it's perfectly okay to treat a pointer to an object that can be modified as if it couldn't be modified. You just refrain from modifying it, no problem. So that is a coercion in C, the type T star to const T star. But still, it treats these as two different types for the purposes of overload resolution. Okay, so that's an interesting little sidelight. All right, now so far I've been talking about explicit definitions of things or implicit definitions of things. Sometimes it's possible to actually infer the type of something from its use and thus avoid the need to explicitly define it. So you still have something that's statically typed. That is, the compiler knows the type of everything, but the compiler can also figure out the type of things without you explicitly telling it. So we call this an inference problem. It's in which we infer the types of things from a set of rules. So let's take a look. This is sort of a classical form for writing an inference rule about types. So if I can tell that in a certain expression E1 has type T1, and I can tell that a certain expression E2 has type T2, if I can determine that, then I'm allowed to infer that an expression E3 has type T3. That's the general form. Now we'll see specific examples where I'm a little bit more specific about what E and T are. And with this, I can define the types of a language. the type system of a language. And I can also give a set of rules by which a compiler might conceivably infer the types of certain things. In fact, we can even use rules of this sort we can even convert rules of this sort into programs that do type checking, sort of like what you're working on now, the parser generator that you're working on now, that converts a grammar into a program that will parse a language. All right, so if we're going to do inference and we're going to be starting to talk about logic-like things, we have to introduce the notion of soundness. We'll say that our rules, a set of rules, are sound if they basically give right answers. In other words, if the rule says that a certain expression E always evaluates to a value of type T, E colon T, then in fact, if you execute a program, E always will evaluate to a value of type T. Now, we want sound rules, but of course, sometimes we have to be a little bit careful not to write a rule that doesn't give us very much information. For example, if E is of type integer, then bracket E is of type, that is, if E is of type integer, then the Python expression bracket E is of type list of E, of int. So imagine that bracket type means list of whatever that type is. Well, that's true, but we can be a lot more general than that. If E is of any particular type of expression, then a list display in Python is going to yield a list of that type of object. We could, rather than just repeat this rule for all the other possible types in Python, of which there are an infinite number, so why would you want to do that? We could write something like this. All right, so let's just look at a few examples of this kind of type definition. If I can show that a certain expression X is of type Boolean, then I'm allowed to conclude that the expression not X is of type Boolean, right? If I can conclude that E is of type Boolean and S is, well, basically void. I think in other languages you'll see the term unit. I'm just using void here, meaning that S is some valid expression or some valid statement that yields, that doesn't have to yield a value. Then I can conclude that that a while statement involving E and S gives me of type void, or in other words, is a valid statement, that it's validly typed. So E has to be of type Boolean for this to work. And I can say that if X is an expression of some type T, then I'm allowed to just write X and not use its value. That's how I will interpret that particular statement right there. So it actually has a technical term. It's called voiding. You do it all the time when you write in Python or C or something like that. When you write F of something as a statement all by itself, then any value that it produces is voided, and that's always valid. There are languages where that's not allowed. For example, in Ada, you can't just say F of 3 as a statement if F is defined to return a value. F has to be defined to be a procedure, that is something that returns nothing. But just to give you some idea of the variations among languages. All right, Fortran, all right, I had forgotten, yes, Fortran also has that same property. Now, what happens if I want to define the type of a variable X? How can I say anything about X's type? how can I demonstrate, for example, that X has type has type int? Well, obviously, if I just ask you, does X have type int? There's not sufficient information to answer that. We need to make this inference on the basis of some hypothesis about the context we're in. So in particular, that we're in the scope of some declaration that has declared X to be of type T. So we'll use the term type environment to talk about what the types are of identifiers are. Okay, now free identifiers is the term free identifier refers to, or free name refers to something that is part of an expression, but where the definition of that thing, where the thing that introduces it is not present. So for example, in the body of a lambda expression, x plus y, if we look at just the x, if we look at just x plus y alone, then x and y are both free. If we have a lambda x in front of it, then x is a bound variable. It's not free in this expression. And y is free because y, there's no definition of y in this whole expression. So, and here's another example, lambda x, gxy, xxy map. So gxy of x, that gives me, applied to x, this x here is a bound variable. This x here is a free variable. And y and g are likewise free. Also, map is free in this expression. So that's just a little bit of terminology. And then we'll use the type environment to give the types for these names. So here's the notation. Something bracket ET means E may be inferred to have type T in the environment O. So a type environment is something that maps identifiers into types. And then we'll need a notation to say an environment which is the same as this other environment, except that I have, except that now Y has type T. So so O of bracket T slash Y refers to just T. If X is, refers to just plain T. If X is the identifier Y. And it refers to whatever the original type of X is, O of X, otherwise. All right, so let's look at a few examples of this. If, assuming that we're in this type environment O, X is of type Boolean, where X is an expression, then in making that same assumption, not X is also of type Boolean. So these are the rules we had before. We just now add on a type environment. Oops, sorry about that. So these are kind of uninteresting so far, but they give you the form. So here's one about addition. If E1 and E2 are both integers, then E1 plus E2 is an integer. And if I is an integer literal, then in any environment O, I is, we can just say that I has type int. Those are pretty easy. Now let's make some use of this type environment. We'd like to ascribe a type to this expression, lambda x colon E1. Now I'll use the notation d arrow t to mean a function that takes a d as something of type d as its argument and produces something of type t. as its result. So that's the type of this thing. So I want to say that this expression, lambda x E1, is of type, is a function mapping D's to T's. Now, when is that true? Well, we have to say that E1, evidently, for this to be true, E1 has got to evaluate to a type T. But, and this is the important thing, when we are looking at E1, we must assume that X has the type D. So that's what it says. If E1 is of type T, assuming that X is a D, then this expression, lambda x E1 D to T, will in fact yield a function of type, the lambda expression will be a function of type D to T. Another way of reading this is if we can infer that E1 has type T in the type environment modifying O so that X has type D, then we can infer that lambda x colon E1 has the type D goes to T. And we can assume that we can make this conclusion using just the original contents of O. So O again is the type environment. That's right. And O bracket D slash X is the modified type environment, which is the same as O, except that we've defined X to have type D. So this course is actually in other years, with this particular project, it used a different language called the COOL language, specifically made for this purpose. An invention of Alex Aiken and his students. And in it, you have an expression that looks like this, the let expression. So this says, assuming that X is a variable of type T0, so X is now a variable of type 0, T0, and we then, with that declaration, we execute whatever this E1, whatever this statement E1 is, statement or expression E1 is, and then return whatever the value of E1 is. So that's what that type rule means. So that's what this is. And the type rule for this is then that I can, assuming, I left off the O in front here, assuming a type environment O, let xt1 in E1 has type T1, assuming that if, wait a minute, we have a slight problem here. All right. If E1 produces type T1, assuming that X has type T0, then this expression here yields something of type T1, except that I see an error here. This should obviously say T0 here, X colon T0. Then let X colon T0 and E1 yield T1. Now, again, I apologize. There seems to be, there should be an O turnstile out here to the left of let X and so forth. Like here, for example. So sometimes you can mess this up very easily. So here's an example of being a little bit too conservative. I want to evaluate, I want to get a value I want to evaluate E1, and after first evaluating E0, And E0 has to be, the value of E0 is assigned to X, and then we evaluate E1. So while we're executing E1, X will be a value of type T0 that's been initialized to E0. So here's a tentative rule. Assuming that E0 evaluates to something of T0, and assuming that if we take X to be a variable, define X to be a variable of type T0 in the type environment, O, the outer type environment, O, if making that assumption allows us to conclude that E1 has type T1, then we are allowed to conclude that the type of this whole let expression, let X T0 gets E0 and E1, we're allowed to conclude that that returns a value of type T1. Now, this is a little bit too conservative. And why is it conservative? What's wrong with it? I mean, it's right as far as it goes, but it's a little restrictive. And can anyone see why? Not transitive. Well, I'm not quite sure what you mean. I think you might be getting at what I want, but there's a little bit more specific. No? So again, as I said, the hint here is that cool is an object-oriented language like Java. All right, well, I'll tell you, the problem with this is that the type of the expression E0 is forced to be exactly T0. But of course, we know that in object-oriented languages, you can have an expression that has some subtype of T0 and still assign it to T0. So what we might want to do instead is to say that if E0 is of some type T2, and that is a subtype of T0, then, and if assuming that X is of type T0, E1 will give us a type T1, then we can say that this whole let expression has type T1. Of course, you do have to assume that subtyping is properly defined somewhere before this will work. And we can also go in the other way. Here's an example of a rule that is unsound. So I'm going to assume that E0 is of type T2, assuming that if E0 is of type, can be shown to be of type 2, a subtype of T0, E1 can be shown to be of type T1, then this let expression yields type T1. What's wrong with this? Do you see it? What is wrong with this rule? Well, I'll tell you what. Why don't you stew on that? Yes, it is in the lecture slides, and you can look ahead, but maybe you should think about it. And based on what you've seen in the slides up to here, figure out why this rule has these two undesirable properties, namely that it allows incorrect program and it disallows perfectly legal programs. We will take this up next time. I will make some, I will modify the little errors that I noticed in the slides, and so that the online slides will have the right answers, or it will have the right things. Okay, I think we're done, and I will see you on, or talk to you or whatever on Thursday. So long for now.